So in the previous lecture, we talked about propagation of light, then shadows, how shadows are formed. We showed varieties of obstacles and varieties of shadows also. We talked about wave nature of light. Light has a wavelength or a mixture of wavelengths. And we also discussed that if the size of obstacle or opening is much larger than the wavelength, then these wave aspects are not prominently shown. And this approximation is known as geometrical ray approximation. And optics discussed under this proposition is called geometrical optics. So in this situation, you can assume that light travels in straight lines in a homogeneous medium until there is some obstacle or some reflector or some medium change or something. It goes in a straight line, which you call light ray. It's also called ray approximation. Now in this ray approximation, the basic assumption is light goes in straight line in a homogeneous medium. That we can see in our experiments also. Now light goes in straight line in a homogeneous medium can be explained, understood just by symmetry of the space. Our space, which I call homogeneous, isotropic, unless there is a material and that material has varying properties in varying positions or in varying directions, if that be the case, then it's a different story. But it's a truly homogeneous isotropic medium or vacuum, and light is going in some direction at some point. Then if it has to bend, in which direction it will bend? All directions are equivalent. Suppose light is going like this in two-dimensional plane, let me talk. So light is going like this at some instant, and now it has to bend. Suppose it doesn't go in straight line. It's all homogeneous medium. Should it bend this way or should it bend this way? All directions are equivalent. All positions are equivalent. It's the same medium everywhere, and the medium is isotropic. Isotropic means all directions are same. So if it is going at certain instant in this direction, should it move this way? Should it move this way? How does it choose between these two if the medium is same? Or similarly, if you go out of this plane, you can have a bent like that, bent like that, so many bending directions you can make. It cannot. So it must continue in this direction. So it must go in straight lines. So many of the physics phenomena can be explained just on the basis of symmetry of space, of medium, and so on, and this is one of them. Now light going in straight lines has a different aspect, interesting aspect. Suppose I have a point A and suppose I have a point B, and the medium is homogeneous, isotropic. So I say that light will take path from A to B, which will be straight line path. It will go like this, not like this or not like this, and so on. Okay, so these paths are not allowed. This path, light takes this path. You can also say that light has taken a path which is minimum of length of all neighboring paths, or in terms of time, light has chosen a path which takes it least time to reach from the given point A to the given point B. Now this simple statement is a great principle known as Fermat's principle. It's not only true for homogeneous isotropic media, even if you have certain lenses, mirrors, some optical elements. Then also if you are given 2 points, it has to choose a path which takes least time. In a given situation, that means all your optical elements are given. What is optical elements? Mirrors, lens, prism, like that. So in a given situation, light chooses a path for going from one point, from one given point to the other given point. So 2 points are given, A and B. Such that it takes least time. Okay, so this is called Fermat's principle. In a given situation, that means with all your lenses and mirrors etc. fixed, light chooses a path for going from one given point to the other given point such that it takes least time. This is known as Fermat's principle, and you apply it here in the homogeneous isotropic medium, it just turns out to be a straight line. There are more fancy descriptions for this principle, but this is good enough. Now the next simplest situation is when light goes in a homogeneous isotropic medium going in straight lines, meets a plane reflecting surface, and then it reflects in the same medium back. Now this reflection of light we are all familiar with. We use plane mirrors and other things, and we see our own images and all that. So there are certain rules for this reflection from a plane mirror or a plane surface, and we will explore these rules. Here you can see we have this mirror, this horizontal surface is mirror, and on this mirror light is incident. This red light you can see, this is incident. It is coming from this laser torch here, it is coming here and then going along this surface of this vertical plate like this, and then it also returns along the surface of the same vertical plane. And on this vertical plane you can see a line, red line that we have drawn. This line is normal to this horizontal reflecting surface. So you have normal, you have incident light, you have reflected light, and all these three are in the same vertical plane made by this plate. So that is first law of reflection. The incident ray, the reflected ray and the normal to the reflecting surface, they are in one plane. And then the angles, the angle between the incident ray and this normal, this angle is known as the angle of incidence. The angle between the normal and the reflected ray is known as the angle of reflection, I and R, and the law says that I should be equal to R. So with these two laws of reflection and doing some geometry, you can easily see how a plane mirror makes images of some objects. So incident ray, reflected ray and the normal to the surface, reflecting surface, they are in the same plane, that is your first law, and I will only show that plane on the board. So my mirror is horizontal, plane of incidence is vertical, and therefore in that plane of incidence you will only have a line of the mirror. So that line I will draw for mirror. So here is that line which I call mirror, and suppose you have a point object here, very small object here, maybe some LED or something which emits light in all directions. Now let me draw a perpendicular, and at the same distance here I just consider a point. At the same distance here, this distance and this distance should be equal. So let me put a point here. Now do this geometry, show that any incident light ray when reflected will go through this point. It is reflected, but if you extend it on the other side, this reflected ray when extended on this side must pass through this, and this is true for all reflected rays. For whatever reflected ray you take, suppose you have yet another incident light here, and then in which direction it will go after reflection? It will go in this direction, so that when you extend it on the other side, it passes through the same point I. I will call this I as point of intersection of reflected rays. The rays are going in this direction, but when you extend, they intersect here. So this point is point of intersection of reflected rays, and that is the image. All reflected rays, they intersect at the same point. So this image, this object here, all rays starting from here, they after reflection intersect at one point, and this is the image of this object. And if you have an extended object, then at this point only those reflected rays will intersect which pass through this, which started from this point of this extended object. If you think of some other point of the object, then all the rays which are starting from here after reflection, they will intersect at some other point, not at this point, at some other point, and therefore you get an image of this quantity somewhere here. So the important point is, for image formation, in that image and in that object there is a point to point correspondence. One point corresponds to one particular point here. All the rays starting from here after reflection must intersect, after extension of course, at that point. At this point only rays which start from here, only they can intersect here, and so on. So that one-to-one correspondence makes the image, and you can do the geometry that your image, the distance of image from the mirror is same as the distance of object from the mirror, and they are on that perpendicular line and all that. Now you know how images are formed, and there is a very simple experiment that you can do to check that yes, angle of incidence is same as angle of reflection, and I will just do that here. So I have this plane mirror here in this stand, and I have two similar pens. So one of the pens I am placing in front of this mirror. So you should be able to see the pen as well as image, and then I take the other pen and I place it on the other side of the mirror, and the orientation should be such that the four things that you are seeing, the two pens and the two images, they seem like two straight lines intersecting each other. So I can change the orientation and make them look in straight line. So image of this second pen and the first pen itself, that should be in the same straight line. That you can see with one eye, you can see that you can adjust that to make it in one straight line. And once you have done that, any of these two you can take as incident ray or incident direction, and the other will be reflected direction. So, if this is your incident direction, this is your reflected direction. If this is your incident direction, this is your reflected direction. And once you have that, you can also draw the normal to this mirror from that point where this incident reflected ray are hitting the mirror. So, from here, from this point, you can draw a normal also. So, you have incident ray, you have reflected ray, you have normal. Now, you can measure the angle of incidence and you can measure the angle of reflection, and then you can verify that yes, I is equal to R within the uncertainty of your experiment, and how well you were able to make that straight lines. So, within that I should be equal to R. So, the next question with plane mirror is, what kind of image is makes? Is it inverted or it is erect? Often you might have seen ambulances, and the word ambulance is written in a fashion that you are not able to read directly. But if someone is driving a car in front of the ambulance and sees the image in that mirror, that person can see a simple, readable, illegible word. So, I have this thing written on the transparency. This you can see this word ambulance here, and in fact the camera is seeing, and it's readable, it's not inverted, it's nicely readable. One, I will show you the image of this formed in a mirror. For that, let me first bring a mirror. So, here is a mirror. I am placing the mirror, and then this transparency with the word ambulance that I will be putting in front of the mirror. So, let me do something. So, I am putting the transparency between these two thick books. So, I am putting it in front of the mirror. You can possibly see that writing on the transparency as well as the image formed in the mirror. Is it inverted? Looks like it is not inverted. The mirror is doing no inversion. Then why the letters, if you write something on a page and take it in front of the mirror, you find it is inverted, and but here I am writing these letters and taking it in front of the mirror and it is not inverted. So, what is happening? The whole problem is from where you see it. Okay? So, that inversion depends on from which side you see it. Take any page, have it in your hand, stand in one side of it and see how it looks. Go to the other side and then see how it looks, and there is an inversion. So, inversion is not because that real material has got inverted or some change has been done in that. It depends on from which side I am seeing. You see from this side and you see from this side. Write something on the transparency and see from this side, see from this side, and you will see that there is an inversion. So inversion depends on the viewer. The mirror is not inverting. It is the viewer which sees the object from with one orientation of the head and the image with another orientation of the head, and that is why that inversion seems to be there. Okay. To substantiate this point, I again bring this mirror here, and let me take an object which is a pen with this green tip here. Right? This is the main body of the pen, and then you have some green portion here. Now in this room, this side is north side. So if I keep my pen this way, the green is pointing towards north. If you see the image in the mirror, in the image also you see that the green is pointing in the same direction. The green is pointing towards north, and that does not change if I view it from here, view it from here, from anywhere. This points towards north, it points towards north, and image also points towards north. There is no inversion in horizontal direction, and there is no inversion in the vertical direction also. If I put my object this way, green is pointing vertically upwards. The pen and the image, in both, the green is pointing upward. The mirror is not inverting the image, not forming the inverted image even in vertical direction. If you are looking for reflection from a curved surface, it's the same rules of reflection that will work. For example, here I have a nearly cylindrical mirror, and this is made from shiny aluminum foil, and see how the image is formed. So look at the image of this laser torch that I have in my hand. If this laser torch is vertical, you can see a thin vertical image, and if I turn this laser torch and make it horizontal, see what kind of image it is forming. Look at this image, look at this image. I am rotating the torch little bit and see how the image, what kind of shape the image has. And if it is vertical, then it is a straight, thin image. You must have gone to science centers, science museum, and in almost all science centers you have mirror room, and if you go there, varieties of curved mirrors are there, and peculiar images are formed, and children enjoy them very much.